When Americans picture the Hoover Dam today, they see a monument of concrete and steel that seems almost immovable, a structure so massive and so perfectly built that it feels as if it has always been part of the landscape. But in the early 1930s, the idea of building a dam of this size was viewed as unrealistic, borderline impossible. The Colorado River was one of the most unpredictable, violent rivers in North America. It flooded without warning, carved through canyons with raw force, and routinely destroyed smaller structures that tried to control it. And yet, the U.S. Bureau of Reclamation insisted that this stretch of Black Canyon could support the largest concrete dam ever attempted. The skepticism was understandable. At the time, civil engineering simply had not produced anything like this before. The proposed dam would rise over 700 feet, hold back the force of a river famous for ripping apart steel bridges, and contain enough concrete to build a two-lane highway from San Francisco to New York. Many engineers argued that the structure would crack under its own weight. Others warned that the concrete would never cure fully, that the heat from its own chemical reaction would take centuries to dissipate, and that the blocks might fracture as they cooled unevenly. This wasn't just a technical challenge. It was a political and economic gamble on a scale the country had never attempted. The Great Depression was at its peak. Thousands of men were desperate for work. The federal government needed a project that would signal confidence, progress, and capability. And yet many of the nation's top engineers doubted that the techniques of the era were sufficient. They were working with slide rules, hand-drawn blueprints, cable cranes, and concrete mixing equipment that would be considered primitive today. Still, the Bureau of Reclamation pressed forward, assembling a consortium of companies known as 6 Companies, Inc. These were the best heavy construction firms in the United States, each one selected because no single company had the capacity to build the dam alone. Together, they represented decades of experience in tunnels, foundations, blasting, and large-scale concrete work. But even they understood the risks. Every component of the Hoover Dam would require new methods, new calculations, and new record-breaking tools. The dam would need to be built faster, stronger, and with tighter tolerances than anything attempted before. In this chapter, the groundwork was set, not just for a dam, but for a test of American engineering itself, and no one knew if the methods would work. To build a dam of this scale in the 1930s meant pushing human labor to its limit. The site sat in the middle of the desert, where daytime temperatures regularly exceeded 120 degrees Fahrenheit. Workers were living in tents when the project began, dealing with dust storms, dehydration, and conditions that would be unthinkable on a modern construction site. Eventually, the government built Boulder City to house the workers, but the work environment itself was still dangerous, relentless, and physically punishing. The first major task was diverting the Colorado River. This required blasting 4 massive tunnels through the canyon walls, 2 on each side, to redirect the water around the construction site. The tunneling work alone was a Herculean effort. Crews used dynamite to open the initial bore, then jackhammers and shovels to carve out the rest by hand. The tunnels filled with fumes, heat, and dust. Many workers claimed the walls seemed to radiate heat like an oven. Yet the tunnels had to be completed rapidly, because until the river was diverted, the dam site could not be excavated. Once the river was controlled, the real work could begin. Workers cut into the canyon floor, removing millions of tons of rock to reach a stable foundation. Men dangled from ropes hundreds of feet above the canyon floor, drilling blast holes into the walls and clearing loose rock. These high-scalers were some of the most respected workers on the site, skilled at moving quickly on vertical cliff faces while clearing potentially deadly hazards. The scale of labor on the project is almost impossible to imagine today. Over 21,000 men worked on the dam at some point, rotating in and out of shifts that lasted 7 days a week. Concrete had to be poured around the clock. Equipment ran non-stop. If any part of the process slowed down, the entire project would fall behind schedule. And 6 companies had agreed to massive financial penalties if deadlines were missed. Despite the harsh environment, the project maintained an extraordinary focus on efficiency and precision. Supervisors meticulously organized crews, equipment, and material flow so that every hour contributed to progress. The conditions were brutal, but the workforce was determined. They weren't building a dam for a paycheck, they were building a landmark that would define American engineering for generations. Hoover Dam's durability is not the product of luck, favorable conditions, or overestimation. It is the direct result of engineering decisions so forward-thinking, so methodically executed, and so unusually conservative for their time that modern engineers still study them today. Everything about the dam, from the geometry of its arch to the chemistry of its concrete, was chosen with one long-term goal in mind: create a structure that would not simply stand for decades, but endure for generations, with minimal repair. To understand why this dam still performs almost flawlessly nearly a century later, we have to start with the central problem its builders faced: heat. Concrete generates heat as it cures, and the Hoover Dam contains more than 3 million cubic yards of it. If engineers had attempted to pour the dam as a single solid block, as some early proposals suggested, the interior would have remained hot for well over 100 years. The curing process would have been uneven, internal stresses would have built up, and enormous structural cracks would have formed. The dam never would have stabilized. It might have failed within its first decade. So the engineers made a revolutionary decision. Instead of treating the dam as a single mass, they would build it from thousands of interlocking blocks, rectangular and trapezoidal segments arranged like a giant three-dimensional puzzle. Each block was poured separately, allowed to cool, and then locked into the structure. This decision introduced a level of temperature control and structural flexibility that had never been attempted at this scale. It turned what would have been an uncontrolled chemical reaction into a carefully managed process. Even with smaller blocks, however, the scale of the dam was overwhelming. The concrete still produced tremendous heat, and the rate of cooling was never going to be fast enough for construction to continue on schedule. So engineers pioneered a technique that is now standard industry practice: internal cooling. Thousands of steel pipes, thin, meticulously spaced tubes, were embedded inside each block. Once the concrete was poured, chilled water circulated through these pipes, pulling heat away and allowing the material to contract evenly. Nothing like this had been done before. It required refrigeration plants built specifically for the project, a network of pumps and valves, and constant monitoring to ensure that temperature changes happened at exactly the right rates. Too fast, and the concrete might crack. Too slow, and the next layer couldn't be placed on time. The entire dam became a living system of heat exchange, a dynamic structure being coaxed and shaped into stability. When each block reached its target temperature, crews pumped grout into the now empty cooling pipes, permanently bonding the segments together. Over time, the blocks interlocked so completely that the dam behaves as a single, unified structure, but one that cooled safely and predictably during construction. The next major innovation was the dam's geometry. Hoover Dam is an arch-gravity dam, a hybrid design that uses both its immense weight and the natural strength of the canyon walls. The arch curves upstream, pressing into the rock faces on both sides. As water pushes against the dam, the force is redirected sideways into the canyon rather than directly backward. This reduces the stress on the concrete itself and allows the structure to hold back staggering volumes of water with far less material than a purely gravity-based design would require. It was an elegant solution, but only if the canyon walls were strong enough to handle the redirected load. Engineers conducted meticulous geological surveys, carving test shafts and analyzing rock composition to ensure the site could support the arch. Their findings shaped the final profile: a thicker base for stability, a thinner crest for economy, and a continuous curvature tuned precisely to the canyon's contours. The result was a dam that works in harmony with the natural landscape rather than resisting it. Modern engineers often point out that the Hoover Dam is overbuilt. Its mass is enormous, its tolerances conservative, and its materials far stronger than required by the standards of its time. But that overbuilding is exactly why it has endured. Many modern dams, designed in eras focused on cost-saving and rapid construction, use thinner sections, lighter reinforcement, and tighter safety margins. These structures rely on computer modeling and assumptions that sometimes fail under extreme conditions. Hoover Dam, by contrast, was designed to be so robust that even large-scale modeling errors would not meaningfully compromise its performance. Another engineering achievement lies deep within the canyon floor, the foundation anchors and grout curtain. Engineers drilled thousands of holes into the bedrock, injecting pressurized grout to seal fractures and stabilize the foundation. Massive steel anchors tied the structure into the canyon itself, preventing sliding and uplift. This foundation preparation created a rock-concrete interface that has remained remarkably stable, even as other dams have experienced foundation seepage and settlement over the decades. The dam's water stops and contraction joints, rubberized and copper elements designed to control movement between blocks, were also ahead of their time. These features prevented water infiltration and allowed the dam to expand and contract with temperature changes without developing internal stress fractures. Many modern dams struggle with cracking because their joints were not designed with the same level of redundancy or long-term flexibility. Even the spillways deserve recognition. They were built like giant tunnels carved through the canyon walls, engineered to handle catastrophic flood flows that engineers hoped would never occur. And yet, unlike many modern spillways that show wear after just a few major releases, Hoover's remain structurally sound. Their smooth linings, curved profiles, and reinforced bases were built not merely for function, but for longevity. When you combine all of these decisions, block segmentation, internal cooling, arch gravity geometry, robust foundations, flexible joints, and oversized spillways, you see a structure engineered not just to survive, but to thrive. Every component was designed to reduce stress, control movement, and accommodate the natural forces acting upon it. The dam does not fight the river, it channels and redirects its power. Nearly a century later, the results speak for themselves. Hoover Dam stands as one of the most stable concrete structures ever built. It defies modern expectations of aging infrastructure, performing more reliably than many dams constructed with advanced technologies. And its longevity is not mysterious. It was engineered into the structure from the very beginning. While the concrete structure is the most visible achievement, the Hoover Dam's interior contains some of the most advanced engineering of the era. When the power plant came online, it instantly became one of the world's largest hydroelectric facilities. But what made it special were the decisions that prioritized reliability above everything else. The turbines were designed to last decades, not years. They were built with precision machining and robust metal alloys, and mounted on foundations engineered to minimize vibration. The generators were similarly ahead of their time, using copper windings, cooling systems, and structural housings designed for continuous operation. To feed the turbines, engineers built enormous intake towers rising from the reservoir, each one housing gates that could be opened or closed to control water flow. The water traveled through massive penstocks, steel pipes large enough to drive a car through, before hitting the turbine blades with controlled force. These pipes were installed with exacting tolerances because even small alignment issues could cause vibration and long-term fatigue. The power plant's control systems were equally impressive. Mechanical governors regulated turbine speed with precision, ensuring stable output even as loads changed. Operators could adjust power generation with remarkable accuracy by coordinating gate positions, flow rates, and generator output. One of the most impressive aspects of the power plant is that many of its original components are still in service today. Some turbines have been upgraded, but the fundamental engineering remains untouched. The longevity of these systems is not luck, it is the direct result of conservative design choices, thick materials, and a philosophy that efficiency must never compromise durability. Modern dams, by comparison, often prioritize cost savings and lightweight construction, resulting in narrower safety margins and shorter lifespans. Hoover Dam represents the opposite approach. Build it strong enough to last a century and maintain it rigorously. Hoover Dam's operational history is nothing short of astonishing. In an era when most modern infrastructure begins showing signs of stress within a few decades, sometimes within just a few years, Hoover Dam continues to operate with a kind of calm, unshakable stability that feels almost unnatural for a structure of its size and age. This isn't simply a case of good maintenance or luck, it's the result of engineering decisions so robust, so overbuilt, and so forward-thinking that even today's civil engineers sometimes struggle to replicate their long-term performance. From the moment the first generators came online in the mid-1930s, Hoover Dam began proving its critics wrong. Engineers who had predicted early settlement, foundation shifting, and widespread cracking watched, year after year, as none of those fears materialized. Nearly a century later, the dam's structural behavior remains almost eerily consistent. The load distribution across the dam's thick arch is stable. The curvature continues to direct water pressure into the canyon walls exactly as designed. The interlocking blocks, each cooled, cured, and set like the pieces of a giant stone puzzle, have not shifted in any meaningful way from the day they locked into place. Modern dams, even with advanced modeling software and improved materials, rarely achieve this level of predictability. Many begin to show microcracking, seepage, or expansion issues within 2 to 3 decades. But Hoover, its cracking is minimal, tightly controlled, and mostly superficial, far below any level of structural concern. The concrete continues to strengthen over time, growing denser and harder as it cures internally. Engineers estimate that the interior will continue curing for another century or more, gradually increasing its compressive strength as it ages. One of the most impressive examples of Hoover Dam's durability is its spillway system. Spillways are often a dam's Achilles heel. They bear the full force of high water events, channeled at extreme speeds that can cause cavitation, a violent, destructive phenomenon where collapsing bubbles literally carve holes into concrete. Many 20th century dams have suffered significant spillway failures, some catastrophic. The 2017 Oroville Dam disaster in California is the most dramatic modern example. A massive section of the spillway simply disintegrated under stress, triggering evacuations and billions in damages. And the painful truth is that Oroville is not alone. Many dams built in the latter half of the century used thinner spillway linings, cheaper concrete mixes, and less conservative safety margins. Hoover Dam, however, has never experienced a spillway failure. Its spillways were designed and constructed with a level of redundancy that seems excessive by today's standards. They were carved deep into bedrock, lined with thick, carefully cured concrete, and shaped to resist cavitation long before engineers even fully understood cavitation's destructive power. It was overbuilt by instinct and experience, an instinct that has paid off. Even after handling some of the highest flood flows in the Colorado River's recorded history, Hoover's spillways show only minor wear. No structural deformation, no major repairs, no hidden damage waiting to emerge. And then there's the concrete itself, a subject that still fascinates material scientists today. Hoover Dam's concrete was mixed with a single priority: long-term survival. The aggregates were chosen for density, the cement content balanced to reduce internal heat, and the entire structure cooled with a massive network of pipes so that it could set without cracking. This produced concrete with extremely low permeability. Water simply cannot seep in and destabilize it, which is one of the leading causes of failure in other dams. Core samples, extracted decades later, continue to surprise researchers. Instead of weakening, the concrete has grown stronger. Its compressive strength is now higher than when it was first poured, and its chemical integrity remains almost pristine. No signs of alkali-silica reaction, no significant rebar corrosion, and no large-scale internal fractures. Mechanically, Hoover Dam has been updated, but only where necessary. Electrical lines have been replaced, turbines have been upgraded to more efficient models, generators have been rewound, bearings replaced, control systems modernized. But the dam's physical body, the enormous concrete monument itself, remains the same. It has not needed reinforcement. It has not required major retrofits. It has not suffered from the fatigue or creep deformation that plague many large concrete structures over time. What's even more remarkable is that Hoover Dam still performs near its original operating efficiency. The turbines deliver reliable power. The penstocks remain in excellent condition. The water intakes show minimal corrosion thanks to the dam's thoughtful use of materials and protective coatings. It is, in a practical sense, a machine built in the 1930s that still runs like a finely tuned engine, not because it is constantly rebuilt or patched, but because the original craftsmanship and engineering were so far ahead of their time. Around the world, civil engineers view Hoover Dam as a benchmark, a case study in what happens when human ambition, careful design, and uncompromising standards converge. While modern dams are often shaped by tight budgets, accelerated timelines, and value engineering compromises, Hoover Dam was shaped by the mindset that failure was not an option. This was a structure built to last centuries, not decades. Its performance record proves that the old methods, patient curing, oversized foundations, generous safety factors, thick concrete, meticulous workmanship, remain unmatched. Engineers studying modern dam failures often find themselves returning to Hoover Dam, comparing its philosophy with today's practices and asking a difficult question. Why can a dam built nearly 100 years ago with primitive tools outperform the structures we build with advanced technology today? Hoover Dam doesn't just run well, it runs almost perfectly. And after almost a century of operation, it stands as a quiet rebuke to the idea that newer always means better. It is the gold standard for dam performance, a living reminder that sometimes the strongest structures are the ones built with extreme care, uncompromising standards, and a long view of the future. Modern dams fail earlier for several reasons, and none of them are surprising to engineers. The first is cost-driven design. Today, projects must be built faster and cheaper. Materials are optimized for efficiency rather than longevity. Concrete mixes cure quickly, but are often more brittle. Reinforcement supplies are lighter. Structures rely heavily on computer models, which can encourage thinner margins of safety. Another factor is regulatory complexity. Modern projects involve layers of approval, design modifications, and environmental constraints that can compromise the ideal engineering solution. Hoover Dam was built during an era when the federal government could approve a concept and let the engineers decide the best method without interference. Construction practices have also changed. Labor specialization, subcontracting, and equipment rental often lead to fragmented workforces and inconsistent workmanship. In the 1930s, 6 companies maintained unified teams under a single leadership structure that enforced precision across every phase of the project. Climate stresses present another challenge. Reservoir levels fluctuate more dramatically today. Hydrological cycles have intensified. Many dams were not designed for the extreme conditions that now occur. Finally, maintenance is often reactive instead of proactive. Hoover Dam has received continuous, disciplined maintenance since the day it opened. Modern dams frequently suffer from deferred repairs due to budget constraints. The result is predictable. Newer dams experience cracking, degradation, and structural stress decades earlier than expected. Today, Hoover Dam stands not just as an engineering success, but as a statement about what careful design, meticulous craftsmanship, and uncompromising standards can achieve. Its massive structure continues to operate almost exactly as its designers intended, a century after construction began. Engineers still study its methods. Universities teach its innovations. Modern megaproject teams analyze its block system, cooling strategy, and load distribution model to understand why it exceeds modern lifespan so dramatically. The dam is a reminder that technology alone does not guarantee durability. Sometimes what matters most is precision, patience, and a willingness to overbuild. Hoover Dam was created in a time when every inch of concrete was inspected, every calculation was checked by hand, and every worker knew that the world was watching. The structure that emerged from Black Canyon is more than a power plant. It is a demonstration of engineering discipline at its highest level. As modern infrastructure ages faster than ever, the Hoover Dam still runs nearly perfectly, proof that some of the strongest structures of the future may be those built with the lessons of the past.